Hello. I'm a PhD student working with Professor Navakanta at Center for Nanoscience Engineering. My talk focuses on continuous electrochemical glucose reduction using ferrocene carboxylic acid chemistry. The overview of the talk would be I'll start with a basic introduction to the topic, including what is blood glucose regulation and what is the need for a continuous glucose reduction, followed by outline of the work where we have done developed test setup. We started our initial approach using commercially available SPs, discriminated electrodes, fabrication of metal electrodes, optimizing sensing chemistry, finally the results, conclusions, and future directions. Yeah. So as you know, glucose is the main source of energy in the body. It is the end product of carbohydrate digestion. And in a healthy individual, the glucose ranges to somewhere from 70 to 140 mg per dl. And there's a mechanism in the body that actually maintains this. So if it's just for a general introduction. So whenever there is increased glucose concentration than a normal level, and a set of cells in pancreas will stimulate production of insulin, which stimulates body cells to either take up glucose or stimulates liver cells to store excess glucose as glycogen, and the glucose level comes back to normal level. In another set of condition where the glucose level falls much below the normal level, alpha cells in the pancreas stimulates liver cells to break down excess glycogen into glucose, and thereby brings the glucose level back to normal level. Now, say there is a condition where there is damage to pancreas, then there is insufficient insulin production or there is no insulin production at all. Or condition where though there is production of insulin, the body cells might be incapable of responding to insulin. So in these conditions, what happens is the blood glucose level doesn't come back to normal level, they stay elevated, and that condition is called as diabetes mellitus, or simply we call it as diabetes. So if you see the blood glucose profile in normal and diabetic patients, uh, the one that is shown in uh, solid line, it shows blood glucose profile in normal individual, which has a constant, which varies within certain range. Whereas in case of a diabetic subject, it sees events of hypo and hyperglycemia. So there are 77 million diabetics in India, and India is home to, it places country in second position in the world. And so what is the issue? What happens when you have diabetes? So whenever there is prolonged glycemic variability, it can cause complications like stroke, blind. I see the, yeah, actually there was an image there which shows different parts of the body. I think it's not visible. Yeah. So stroke, blindness, heart attack, kidney failure, amputations. So all these are the complications that are resulted due to prolonged glycemic variability. And these complications can be prevented or at least delayed if we try to maintain glucose levels as close to healthy levels as possible. So for this, we need to monitor glucose continuously, and that is where a continuous glucose monitor comes to picture. So which can give us real-time glucose measurements, which can improve the quality of life of patients by reducing the events of hypo and hyperglycemia. So if you see the red dots here, it shows the finger prick test that people usually do. Maybe you can prick your finger 3 to 4 times a day. And if you see the blue line that is shown here, it shows the data from a continuous glucose monitor. So the events of hypo and hyperglycemia that are missed with traditional glucose test can be picked up when you have a continuous glucose monitor. So that is the overall idea of why do we need a CGM or a continuous glucose monitor. And our work focuses on developing an electrochemical glucose sensor, basically a second generation sensor where we use a mediator to shuttle electrons and with minimal interference, and mostly focusing on the cost effectiveness and ease of sensor preparation. Yeah, so we have four major work portions that we have divided our work into. So one is the development of a 3D printed setup for the flow of analyte. We started with commercially available SPs and then moved on to fabrication of the electrodes, optimized sensing chemistry, and then finally the continuous glucose monitoring. So this is the first part where we have developed the test setup. So this is a 3D printed test setup. I don't know if you can see it. There's a through hole in the setup, and just a minute. Yeah, there's a through hole in the setup, and there is a slot for electrode insertion. So we fill the setup with agar gel, and we make a channel through the setup for the flow of analyte. The sensor along with the PCB is inserted beneath the channel within the gel, and we connect the entire setup to a syringe pump, So changing the glucose concentration within this range, we will have a way to continuously flow the analyte without disturbing the setup. And yeah, so it also mimics the like our aim is to have a sensor that picks up glucose from interstitial fluid. So by this way, what we have is the glucose flowing to channel is slowly diffused through the gel and reaches electrode surface. By that, we have a we can mimic the real life scenario how the glucose diffuses from the capillaries to the electrode. So initially we started with the ferricyanide chemistry on SP. So ferricyanide, as we know, it is the most commonly used mediator on blood glucose sensors, but it is for one-time sensing. So you take a strip, you measure your blood glucose, you throw away the strip. So first we started with that ferricyanide chemistry and wanted to move on from one-time sensing to continuous sensing. So with one-time sensing, we got a response for different concentrations. Now the point was to move from that to continuous. We optimized the cross-linking chemistry with glutaraldehyde linking and albumin. And with that on SPs, what we saw was there we have chosen two different glucose concentrations, a low and a high concentration. And what we saw was the sensor was responding to changes in glucose, but there were challenges. So one was detection potential was high, around 0.55, 0.60, and the mediator leaching was very obvious. It was visibly seen. The leaching of mediator was seen, even though sensor responded. So to overcome these two challenges, one thing what we did was the sluggish kinetics on SPs are very well known. So we wanted to move on from carbon electrodes to metal electrodes, and then the mediator leaching. So instead of having just physical entrapment, we wanted to choose a mediator which has a easy linking functional group so that we can link it to the enzyme. And this is the fabrication part where we have chosen silicon substrate using the simple shadow mask technique. We have deposited metal and the shadow mask used and the 3 electrode configuration of the electrodes we have used, and we have tested that. So cyclic voltammetry with standard redox molecule shows the capability of our electrodes to detect the redox activity, and thereby one simple step for fabrication process can actually give us electrodes for electrochemical sensing. However, this is just a starting point. We are also working currently on miniaturization of sensor using lithography process and choosing alternative substrates other than silicon. And then, yeah, as I told, mediator leaching was a very big problem because having a gel or having a chemistry that can stay on the electrode surface for several days is a problem. It's not an easy task. So we started with a mediator molecule that contains functional groups which we can link covalently to the amine groups of the protein, and then further cross-link it with albumin and glutaraldehyde. And with that particular sensor, we got response for about 1 hour. The first two graphs that we can see here for two different glucose concentrations, 50, 300, 50, and 300. And the last two that you can see is for 3 hours, response for 3 hours. So if you compare it with the previous data on SPs, the current values were very stable and consistent. And also the technique was not very, we didn't use any extensive synthesis procedures. So by that, the technique was simple. And choosing a right detection potential was also a study. So we varied the potential, we measured the current response at various potentials and saw that beyond 0.35 volt, we didn't observe any improvement in currents with the increase in potential. So we chose 0.35 volt as detection potential. And with that particular voltage, till now we saw how sensor responded to two different glucose concentrations. We now wanted to see whenever there's glucose fluctuations, just like in real life scenario, how our sensor responded. And that is the graph, the second graph. We started from 0 at PBS buffer, then 450, 400 mg per dl, back to 200, 150. So we repeated that like around 3 times. That's about 3 hours of duration, 3 to 4 hours of duration to see how our sensor responded. After that, we dipped the sensor in 100 mg per dl and saw what is the consistency of the current values. So we got a very stable data up to at least for a day. Okay, and this is the operational stability and interference study. So the first graph here shows the current response of the sensor at 0.35 volt for one given glucose concentration for about 7 days. So if you can see from day 2 to day 6, the current values were very stable, and by the end of day 7, the current dropped by 12%. And Yeah, so in this study, each day we used to measure and half an hour, and between the days we kept the sensor dipped in buffer. The last one is the sensor response in presence of interference molecules. We saw just 1 to 7% of variation in the presence of interference molecules. There was no much effect of interference molecules. And yeah, to summarize, we have developed a setup, initial experiments with SPs, transition to metal electrodes, optimize the chemistry, and evaluated response to 1 to 7 days. Currently, we are also working on miniaturized sensor and evaluating its in vitro and in vivo response in mice model. Yeah, so this is my group, and I acknowledge, I thank NNFC and MNCF for the facilities provided, and yeah, SENS and the IEEE EBSCON for the.
Thank you, Kavya, for that.